Welcome everyone. Thanks for being here for the second of our events in the Data for Good event series. For those of you who haven't made it to the first event a couple of weeks ago, what's the idea behind this series? The idea is that for some, if not like much of the work that you do as a data scientist, there is the hard work that you don't see in publications, in products. And when it comes to particularly products for the common good, like there are rival goals, right? So you want to be productive, but also you want to be transparent. You want to be like reproducible. You want to have a workflow that you're happy to share with others. Okay? And in practice, that comes with challenges, depending on the topic, also with opportunities. So the idea of this series is to make some of that work visible, also like to provide it with some guidance and like how to do things, really, some of the stuff that you don't learn in the regular curriculum. And for today's session, we have Max Callaghan with us. I'm very happy that Max agreed to take over one of those sessions. I think some of you, if not many of you, already know Max, but I'll nevertheless give him a full introduction. So Max is a researcher at the MCC in Berlin, Mercator Institute. I've got to look up the entire Mercator Research Institute on global commons and climate change. Max received his PhD from the University of Leeds in 2022, and his research is on, well, climate change broadly speaking, but also the scientific debate on climate change and how we can systematically assess it, measure it. And research output is mostly text. So Mark is working a lot with the text and has innovated text-based research on evidence synthesis, really. Papers of his have been published in journals like Nature Climate Change, Environmental Research Letters, Nature Energy, The Lancet, just to name a few. So it's really impressive. And yeah, I guess today's talk will be about like how to get in those journals at the end of the day. So let's all learn from that. Max, thanks again for being here. The floor is yours.
Yeah, super. Thank you very much for the introduction. Okay, so yeah, the way I've set up this tutorial or talk or whatever it is, or is as a tutorial. And what I've done is basically I've taken one of my papers, and actually speaking of rival goals, it's one of my papers that was supposed to submit at the end of last week, but then I started making a really reproducible workflow for how to do it, so I haven't submitted it yet. But we do have some products available from this paper. So I'll show you this link here, which is basically an interactive map of the literature on climate policy instruments. And I'll go into that a little bit in more detail later, but this is basically the end goal. This is what this paper produced. And we're going to go in this tutorial, which you can find online. If you just follow this URL, it's probably too small to follow, but it's mcallaghan.github.io/ml-map. But no worries if you, well, I can send you the link later. I'm going to show it to you now, so you don't need to see it otherwise. Okay. So as I said, we're going to go through all the steps to reproduce that map. And I've kind of structured this in kind of form of documentation of the code. And maybe just before I kind of go into it, I'll talk a little bit about what you need to do to reproduce this code, should you wish to do so, although you don't need to. So one thing that we need to do, especially if we want to have reproducible workflows, and we're working in Python, and this is exclusively in Python, this work, we should create a virtual environment, which those of you who are familiar with Python will know that it basically says, make a version of Python with the packages that I want, that's kind of isolated from the normal Python that runs on the system or from any other version of packages of Python with different sets of packages. And it says, okay, when I run Python inside this environment, then these packages are installed. And this is very helpful for making us reproducible. So we just need to make a virtual environment like this. And then we need to install the requirements in that Python environment. One of the larger ones is something called Torch or PyTorch, which is one of the large machine learning libraries. There are just some instructions here that, depending on whether you have GPU resources or not, there are different ways to install it. So just follow this link and that will tell you how to do it. That would save you, everything will run faster if you have GPU resources, but if you don't, then you don't need to take up so much space when you install and then you just need to install the remaining requirements like this. This should actually say requirements.txt, but it refers to a file that's also in this repository. You can see, by the way, link to the repository here. I hope it works. Yes, very good. There you see there's a file here called requirements.txt, which just says all of the different packages that we need. I'll go back into here. And we also need to install this package. This should actually be a little dot there. I just saw this. But basically it says install the file, install the package that's described here, the code, the functions that I've described in here. And then if we want to recreate then what's in this tutorial, which is basically lots of notebooks where I talk through the code that that I've written to reproduce this, then we just need to build the documents using something called suites. Okay, then that is basically it for the kind of setup stuff. You can kind of refer to this later. You don't need to install all of the documents. The documents are actually just a way of kind of showing the code in a kind of nice way, but there are also some, as we'll get to later on, there are some kind of, we can reproduce kind of all of the analysis by running a couple of scripts, which I'll show. Okay, so much for that bit. Okay, so let's talk a little bit about what we're actually doing here. So Simon's already talked about evidence synthesis, which is basically the practice of doing research on research results. And the reason why we need this, and this thing especially for a school like the Hertie School, why we need this that's kind of focused on how the relationship between science and policy is that we shouldn't do evidence-based policy making on individual studies. Because if we wanted to show a certain narrative about the technological transition, we could find a study that would show that fuel cell vehicles, shifting to fuel cell vehicles really reduced carbon emissions, and shifting to electric vehicles really increased carbon emissions. And some people do cite these studies, and you'll hear certain German economists, for example, famous ones with strange facial hair, repeating the fact that, of course, if we use electric vehicles, then we're actually going to increase carbon emissions. And there are studies that show that. But if we look at the whole distribution of studies, then we can see that actually these studies are outliers, and actually we need formal methods to identify all of the relevant evidence, critically assess it, and synthesize the results. So this is just, this isn't a formal method to synthesize the results, it's just showing the spread, but what we're going to focus on today is actually more about the formal methods to identify, and actually all of these are important. So we need formal methods to synthesize results, formal methods to critically assess, and also formal methods to identify and research. So that means that when we do kind of formal evidence synthesis, we don't just kind of look on Google Scholar, I found some papers, and then those are the papers that we synthesize. We actually have to look more systematically for those papers. Yeah. Okay. Oops. So there is a kind of discourse that has come into being fairly recently, not too recently, but over the last couple of decades, I guess, that's about machine learning for evidence synthesis. And the reason why this has come into being is because evidence synthesis can be time consuming. And so traditionally we'll search multiple databases and we'll review every document that matches our query by hand. So often we'll have two people looking at every document, and each person was saying, okay, so we're doing this review on the effects of electric vehicles on carbon emissions. Is this paper about it? Okay, I'm reading the abstract. Does it meet our kind of inclusion criteria or not? And if we do this for thousands of papers, then this takes a really long time. We have more and more thousands of papers. And this is now quite an old graph from one of my earlier papers, where we just looked at how many papers there were on climate change. And there are lots. And for an organization like the IPCC, who has to comprehensively assess the science of climate change, this is quite a big challenge, because in the first IPCC report, they had about 1,000 papers to assess, so they could just read them and assess them. And now we have, in the last assessment period, which is now finished, we had about 350,000. So no one can read all of those papers and assess them just like that. So there are a variety of ways that machine learning can help to substitute some of that human labor and kind of be a complement to some of that human labor in the evidence synthesis process. And there are lots of different applications. I just put a link to one report that detailed some of these, but there's just to say this is quite a big area, and then we're going to focus only on one specific aspect. Okay, so what we're looking at here is machine learning assisted systematic maps. So this is a kind of slightly newish category that we've kind of invented a little bit, which is basically systematic maps. Those exist, and they are forms of evidence synthesis which aim to map out what has been researched in a particular domain. So not to say what does the research tell us, but what do we know about this research topic? How much research do we have on this thing and that thing and this thing? So it's just about this identification part. So it's quite descriptive. And typically these have been rather narrow in the past because of the kind of labor intensity of producing such things. But with machine learning, we have the opportunity to map out entire research fields, like climate impacts research or climate and health research. I've given a couple of examples there, but another one is the COVID. There was a systematic map on COVID research, which was also using machine learning. And there's basically, they wanted to keep kind of track basically of all of the papers about COVID. And okay, these ones are on this this type of treatment, these ones are on that type of treatment, these ones are on this outcome. And they basically wanted to just keep up to date this map of the literature to allow researchers to then say, okay, I'm interested in this thing and this thing, then I can kind of do this kind of synthesis part from here and kind of already have this started. Or to say, okay, should we do a systematic review on kind of this set of subject, this set of topics, so this treatment, this outcome, or is there actually not enough research yet? So it kind of informs kind of decisions about kind of doing further evidence. Okay, so this takes us to the project that I started with lots of co-authors actually a couple of years ago. I still need to submit it. But basically to kind of give the motivation, we are not on track to meet ambitious climate targets. So this is a graph from the latest UNEP GAP report. And if we want to get to keep warming to well below 2 degrees or 1.5 degrees, then we need to reduce emissions that much, this green line. The 2 degrees would be this blue area. And actually, where we are, depending on how you count up what people have promised they're going to do, what people have already announced they're doing. We're kind of somewhere in this area. And you can see the date here, this is 2030. That's actually just 7 years away, 6 years away now. So that's very tricky. And if we're going to make progress, then we're going to need to learn rather fast about what works under which conditions and why. And we know there's already quite a large literature on climate policy instruments, but it's also really widely dispersed and hard to systematize. It's multidisciplinary, and kind of climate instruments are also just a mass. Climate policy instruments are a massive topic because climate policy instruments deal with many different sectors. Got lots of different types of policy instruments. There are lots of different outcomes that you can analyze, so how they reduce emissions, but also the social outcomes. It's a massive, massive area. And so we tried to systematize this a little bit. So one thing we do first is that we made this kind of nice typology of climate policy instruments where we said, okay, let's break down these different instrument types into how the instrument does what it does. So we have agreements, economic instruments, governance strategies and targets, information, education and training, and regulatory instruments. And then within those, then we have lots of subcategories, and within those we have lots of subcategories. Yes? Yes, we made these manually. So we kind of sat down. Christian Flaxland is also one of the co-authors on this paper. And we sat down and basically discussed it. There are some existing typologies of climate policy instruments, but we felt that they were limited in certain ways, not comprehensive in some ways, not consistent in some ways. And we really tried to follow this process of, okay, how is the instrument doing what it's doing? Because sometimes then there was spending money on research was put as a kind of education, information and training instrument, but then we felt, okay, but how is it actually doing that? It's by spending money on something, it's by giving money to researchers. So we then put it in economic instruments, but actually we could argue about these different definitions for a long time, and reasonable people can disagree. In the end, we felt like this was a nice typology, and also making this typology also helped us to kind of get a kind of mental model of the literature that we were interested in. Okay, so in the paper, what we do is we kind of classify, we identify which papers are about climate policy instruments. We classify them according to this typology, also according to the sectors and the countries that are mentioned. And in the paper, we also then do some analysis where we compare this to the distribution of policy instruments and the distribution of emissions. But the data set itself is also quite a nice thing. And what we're going to do is in this tutorial, just go through the process of producing this data set and also of making it explorable. Okay. So, okay. So the first step is acquiring data. And I don't go into this in a lot of detail. But the data comes from OpenAlex, which is a, I can follow the link and show you. It's basically, oops, we'll leave this page, let's down here. It's a large database of, it claims to have almost all of the research, probably it's missing loads of stuff, but it's basically, there have been bibliographic databases for some time, and there are proprietary ones like Web of Science and Scopus. There used to be one called Microsoft Academic Graph, and then that stopped. OpenAlex restarted that effort. There's Google Scholar, of course. But what OpenAlex do is they kind of make it a little bit easier to access the data. So with Google Scholar, it's very easy to use to find 1 or 2 papers. But if you want to have a kind of transparent query, you can't do that because you don't know how the algorithm works. And if you want to retrieve more than 1,000 records, you also can't do that. But with OpenAlex, you can do that. They have an API. I've just, in another tutorial, I went into more detail on how to use that API. You can follow that link if you're interested in doing that. In the case of this paper, we didn't use that API, but actually there's another thing that they allow you to do, which is to download the whole snapshot, so all 200 million records, and update this every 2 weeks. And then, so we've got that on one of our servers, and we use something called Solr, which is like an Elasticsearch type thing that allows us to then query the database. And we then have the whole database at our fingertips, and we have like control of how that works. But I won't go into how you do that because that's basically, it's a nightmare, and you need lots of computational resources. So then from this massive database of 200 million papers, we extracted, using a query that we'd used for other papers before, those that are about climate change. So basically, this is just a long list of words that are somehow about climate change. I should note that this means that we don't have the full universe of climate policy instruments because, for example, a congestion charge may have effects on greenhouse gas emissions. So we also include greenhouse gas emissions there. But a congestion charge may be, there may be a paper about a congestion charge that doesn't address either greenhouse gas emissions or climate change, but that policy instrument is still affecting climate outcomes. And if that paper was about the kind of distributional conflicts involved in implementing this congestion charge, or if it measured how traffic volumes responded to that congestion charge, that's super interesting for us if we want to know what climate policy instruments work, but it doesn't mention climate and it doesn't mention emissions. So we don't find that paper. And we can't really have a way around that because in the end, the system boundaries are just so difficult to draw clearly because then, so one of the databases kind of claimed to capture everything, all policies that affect greenhouse gas emissions, but then that's impossible because the lockdown policies in COVID affected climate greenhouse gas emissions more than any other policy we've ever done, basically. And that's not a climate policy, or is it? And in the end, we kind of get completely stuck and we have to say, okay, for clarity, this paper has to mention either greenhouse gas emissions or climate policy, or there's this limited subset of things like a carbon tax where basically there's no reason to do a carbon tax apart from reducing emissions. There's no other possible motivation for doing that. Okay, so there's just a note on the system boundaries. And these look, I've put these in the data folder of the repository. Slightly worried about that because I included the abstract, but OpenAlex, when they give you it from the API, they kind of scramble the abstract. I never really understand why that is. There's something to do with copyright, and it's easy to descramble the abstract. Just for the easiness' sake, in this tutorial, the abstract is not scrambled, but maybe it should be. I'll have to just think carefully about the copyright implications later. But I think I just make a small sample of the data available, so hopefully no one's going to see. So this is about 50,000 papers that are on climate change. This is less, I think it's 5% of what we found in that query. So that query found really loads and loads of stuff. This is a small percentage. And you can see that each paper has an ID, a title, an abstract, publication year, a type, and a DOI. Okay, so let's get to labeling data. So this was a very laborious task, as I already said. We spent months reading abstracts by hand, and this was the kind of platform that we made for doing this, where you'd kind of click on, you'd go to this website and you'd say, okay, now I have 50 articles to code. You'd click on that batch of articles, and then you would see this. Okay, Ghana's bioenergy policy is 20% biofuel integration achievable by 2030. And so here we decided, yes, this is relevant. It's about climate change. It's about mitigation. It seems like we missed this bit, but no, that doesn't matter. It's about governance strategies and targets, planning, targets and goals, and it's national. And so we'd have to do this many, many times. We managed to code about 2,500 in the end. Yeah, and I've made then a subset of these, just 1,500, available here. And you can see that the outcome is, again, the ID, title, and abstract. Then we have a load of variables here. Include is it included or not? Then all of these columns that are beginning with 4 are the policy instrument type. And all of these columns beginning with 8 are the sector. So this is also just a subset of the total number of labels that we coded. But I also should say that those really kind of subcategories, and also a lot of the subcategories, we had few examples of them, and so our classifiers couldn't reproduce them very well at all.
Let's just briefly on the labeling workflow, because some of you might consider labeling data for your thesis and stuff.
Mm-hmm.
Like there is some, like before you actually start the process, like there's some calibration to be done, and like developing the scheme, and then to figure out how consistent labels are. Like just like what are your experiences in that? Like how did you like set this up? Also like the website component. It's like just like when I do stuff like that, my go-to tool is annotate, but I just use the sandbox and then let other people work on it. If you set up your own website, or like you can share a little bit more.
Yeah, I mean we kind of started this process. I think probably about 2017, before I started my PhD at NCC. I was there as a student researcher. And then we had one project where we wanted to do a systematic review. And then we started getting a load of spreadsheets, and then it quickly became very tricky. And then I thought, okay, I'll just make something. And then it just spiraled completely out of control. And we ended up with this kind of labeling infrastructure, and people would keep saying, okay, I want it to have this feature, I want it to have that feature. And it got really big in the end, but it's basically this website that we showed then. And one of the nice things about having our own system, because other systems are available, is just that we had like flexibility over everything. Like if we want to say, no, we want it to look like this, or to have this type of label. And we had the case where if you clicked on governance strategies and targets, then only those subcategories that were under governance strategy targets would appear, and then lots of other stuff. And then at some point we were like, okay, but what if the document is about this label, but only a little bit? Can we also like click on it twice and then have a different thing? And then all of this stuff, we were able to do that. Also, we were able to get the data and kind of just query the database, and that was nice. Yeah, so that's on the kind of infrastructure part. On the kind of social process, what we did is we had like a kind of some coding in the round, like with like all of the coders, where we kind of iterated on the typology, looked at whether we were agreeing or not, and just kind of went over things for a couple of weeks. And then we went down then to double coding. So we'd have 2 people coding each document, and there'd be like, then it got complicated, because then say you could code 40 documents, and Amin could code 80 documents, and Justus could code 20 documents. Then we'd have to allocate those somehow, and then organize then the kind of the what's the word, where people disagree, then we'd have to find the thing that they agree on. Resolve the conflict, that's what I meant to say. We'd have to resolve the conflict, we'd have to organize all of this, and then we'd have like weekly meetings when we'd say, okay, and me and Justus, we couldn't agree on this document, what does everyone else think? And yeah, it was super labor intensive. But it means we have it's nice to have double coded data and also high quality coded data, because I think we could have also sent this to Mechanical Turk, but then that's also like quite specialized as well. Like, is this a quota? Is this a tariff? Like, it's kind of, we needed some expert knowledge. Yeah. Okay, good. Yes.
So like after labeling,
No, only 2,500 documents.
Okay.
So it took so much time, we only managed 2,500.
Okay.
But we spent about 6 months.
Okay.
We probably spent a load of money on it.
But like people use like that type of model.
Yeah. I mean, let's talk about that at the end. But that's a big something we're actively exploring. My boss is more enthusiastic about it than me. I'm slightly more skeptical about how well it will work, and I want to evaluate it very carefully. Yeah, but I don't have to apply for the funding that says how much budget we have for doing the coding. Yeah. Okay, so one note here is that a kind of slightly additional complicating factor was that because we had only some labels of some classes, we did some, and also because the minority of the documents in our data set were about climate policy instruments, we didn't only code at random. So we didn't only randomly select papers from the data set. And in this tutorial, we'll treat them as if we did. Because if we kind of analyze how well our model works on the data, that data that we're analyzing, it should be representative of the data that we're applying the model to. So what we did was that we made sure that anytime a non-random document was in the test data set, then we would kick it out. So we'd make sure that but it gets too complicated to show how to implement all of that. Just to know, we're treating it as if they were random. Okay. So we have a couple of different labels that we see here. One is inclusion, and you can see that the minority were included. If this was the representative sample, this would be way down there. And then of those ones that were included, these are about different policy instrument types. We don't have many for information, education, and training. And these are about these different sectors. So these are basically the IPCC mitigation sectors. And one cross sector was just basically if something just talked about emissions reductions without saying in the buildings or the transport sector, we'd just use this label. Okay, yeah, this is just another plot of how many we have on the different combinations. And this is quite nice then to see, okay, we have this many types of this instrument on this sector, and we could see some interesting things about some different patterns in there. But I will skip that. Okay, so now this is the kind of the meat of the tutorial, which is about how we train and then use this model. So we're going to go through all of the steps to go from that data set that we've just seen into a data set that includes then all of the papers that we haven't seen and what we think they might be, how we think we would have coded them according to our model. So the first is a small intro to BERT and transformer models, a very, very short introduction. Just to say that before large language models came along at the end of last year, BERT were the last thing to kind of change how we did lots of kind of work with text in the social sciences and also more broadly. And to put it very, very simply, it's trained on lots and lots of documents to predict missing words. In doing so, it learns a representation of text that's useful for other tasks, and we can use it for other tasks, such as classification, if we show the model examples of documents that are in one class or another. That's all I want to say on BERT for now, but there are plenty more resources, especially this one is quite a nice accessible resource for doing something, for understanding BERT. Okay, so now we're going to go through the steps of how we fine-tune a BERT-like model using Hugging Face, which is a platform that hosts thousands of pre-trained models, as well as libraries and resources that make it easy for us to fine-tune it. So fine-tune, by the way, is that process that I referred to before. So we take a model that's already been trained, we show it some examples, and we fine-tune it to learn how to classify those examples. So this code below will run much faster with GPU availability. I don't have it on my machine, but I used one of the computer we have in the office. And if you want to run the code, but it takes too long, or you have memory issues, you can use something called BERT Tiny, which is like a very tiny version of a BERT model, and everything will run much faster, but the quality won't be as good. But in the end, we're just trying to understand how it works. That's also fine. And also in the background, Transformers uses either PyTorch or TensorFlow, and we're going to do this with PyTorch. So the first step is to get our data. So here we've shown just a small sample into the Hugging Face datasets format. So here I just printed a few title values and a few include values. So here we can see the pitfalls and promises of climate adaptation planning is not a climate policy, climate mitigation policy instruments, policy instrument. So this is only climate policy mitigation, not adaptation. Impact of CO2 emissions on low volume road maintenance policy, case study of Serbia. That was a climate policy instrument. Also, research on emission reduction in supply chain under the energy performance contracting mode. Okay, so we have a couple of examples that were relevant in there. And we just need to put those into a data set, the text, and a label. Then we need to tokenize, which basically takes those texts that we've passed, that we've just had, and kind of prepares them for how the model wants to, is ready to kind of accept them. Here, the example, we need to already name the model. So here we're going to use Distill Roberta Base. You can also change and use another model. This one is quite an interesting one that's trained on climate text, climate BERT. And we just we run these texts through the tokenizer function, and we end up then with a data set that has text labels, input IDs, and attention mask. And to make this a little bit simpler when we do it, there's a little function that I've made to take a data frame that has a text and a labels column and put it into a Hugging Face datasets. So here we have a nice little link. We'll see if it works. And here we see all of the source code here is in this reference section. There's quite a minimal documentation for some of these, but you can look in source and you can see that, okay, this is actually what we do. This is the code in that function. So I've tried to put links to the function that we use as much as I can. Yes, so when we want to train our model, we use this thing called a trainer, which is a utility from Transformers, which is the Hugging Face library. And we train a model with a training data set. And then this, you'll get a kind of progress bar that goes along. It can take some time. And we end up with a trained model. So once we have a trained model, then we use it in order to make predictions. Here's how we do that. We need to, here's an example with some new text that I just made up. We put this into a data frame, then we tokenize it and put it into the Hugging Face format. And then we just run train and predict on this data set. And you can see that we have an output here. The predictions are minus 0.8, 1.1, 2.56, minus 1.94. So at the moment, that doesn't tell us very much. We need to process these a little bit further. These are logits, which are the kind of outputs of the model. But we can turn this into probabilities or something that are quite close to probabilities, although we can't always interpret them as strict probabilities, with an activation function. Just on the structure of this, each of these pairs of labels, there's a label for the class 0 and a label for the class 1. And this is for the second example, the label for the class 0, which is not include, and the label for the class 1. And if we have kind of two different classes, then the softmax function ensures that the probabilities for each class add up to 1, which is useful if we have, it can be in one of those classes exclusively, can't be in both classes, can't be in 0 classes, it has to be in one of them. Then if the probabilities add up to 1, then the probability that's above 0.5 will be the class that we think belongs to this document. So if we put this through a softmax function, then we get the following output. So remember, the first one was designing effective and efficient CO2 mitigation policies in line with Paris Agreement targets. So I just put as many keywords that made it sound like a climate policy just to make sure it worked. And climate model derived anthropogenic forcing contributions to hydrogen intensity. And here our model has learned that, the first one is likely to be, highly likely to be included, and the second one is even higher likely to be excluded. So it works. Good. And one thing that we do is we subclass the trainer class to give it a predict proper method. So what does subclassing the trainer class mean? Well, basically that link didn't work. What we do is a class is a type of Python object that does some things. It takes in data. You can do methods with that thing. And if you subclass a class, then you say, I want this new class to be exactly the same as the old class, but I also want to define some new features for it. So we take the training class that we already had, and we add a new feature, which is to do probabilistic predictions. So it just makes it slightly easier for us instead of having to kind of put it through this different function each time. We can define a function that says, okay, just do it. Okay, so what if we want to do multi-label predictions? It's very similar. All we need to do is we need to construct this labels variable slightly different. So the way I do it here is I define this thing called the Y prefix, which is basically because all of the sectors begin with 8 and a dash. Then if I say the Y prefix, then the targets that we have are all of the columns that begin with an 8. So we just turn this into a kind of array, basically, and then pass that to the model. So this is what the labels variable looks like. And now we've also trained a multi-label classifier. We need to use a slightly different loss function, but you can look in there if you want to go into the details. I don't think we need to do that now. And here we can see, okay, if we put in some new text, optimal CO2 pricing of light vehicles, trucks, and flights, blah, blah, blah. This one is about transport. The Paris Agreement and its implications for land use, forestry, and agriculture has correctly been identified as being about AFLU, which is agriculture, forestry, and other land use, I think. Okay, good. So now that's the kind of half of the work done. We've learned how to train how to fine-tune a BERT-based model. But we can do this in various other ways. So the model we've just trained, it works, it's okay. But there are other choices that we can make about how we set up this model beyond simply using the default parameters that we've done. So we've actually made a choice before, which was to use the default parameters. And these choices that we can make will affect the performance of our model in ways that we don't know. So it is likely that the default parameters are not the best ones, because the best ones are dependent on the structure of the data. So it's not that there's a universal best set of parameters, otherwise we would always use those ones, but actually we don't know unless we try. So the original BERT paper suggests these different parameters. And if we look at the unique combinations of those parameters, so this is just, yeah, let's not go into them in too much detail, but basically we have 18 different combinations of those parameters. And so if we wanted to check each one of those, we would fit that model 18 times. So that's already quite a lot of work to do. But let's just first look at how we would do that and how we would see if that model is working or not. Because before we just used a heuristic, we made up some new text and said, are they right or not? But we can do this more formally because we have lots of labeled examples. So what we're going to do is we're going to separate some of those documents from we're going to separate them into the documents we're going to use for training and the documents we're going to use for testing. So we'll train a model on a training data set and test it on our test data set. And we'll see how well does it predict the test set. Okay. So what is in here? Yeah, here we just split the training and the test data set. And we can, from this original data set that we have, we can construct another one, train data and test data, just using the select function. And this is just the index of the data frame. So to set hyperparameters for a model, we need to use this training arguments class. And then we'll say P is the first item in our list of unique parameter combinations. And then for each key value pair in P, we'll set the attribute key of training arguments to value. So we'll say the number of epochs is 2, and the learning rate is whatever. Then we just train the model with these training arguments and args as args. And now we have trained a model with some hyperparameters, just one or 18. And if we want to see how well it works, we can calculate the F1 score, which is the harmonic mean of precision and recall. I'm assuming you know that, what those both mean, but please ask me if not. And we can also see a confusion matrix here. So actually on this small example, we haven't done very well because when the true label is 1, we always predict 0. And when the true label is 0, we also always predict 0. In fact, we're always predicting 0. However, that does mean that we have an accuracy of 60%. So that's not too bad. Okay, so one other hyperparameter that's not in the set of default hyperparameters is called class weighting. And this basically the optimization procedure. It cares just as much at getting a 0 wrong as it cares about getting a 1 wrong. But actually, we might have good reasons to care more about getting a 1 wrong. And so we can just make it more expensive to get a 1 wrong than a 0 wrong. So all we need to do is calculate some weights, which is the number of documents in the data set divided by the number of documents that are in each class. So the more documents are in one class, the less expensive it is to get that class wrong. Yes. Okay. So if we want to implement this, then we need to subclass training arguments to allow us to put these this kind of new set of hyperparameters in. And then we can say class weights as weights and use class weights as true. So we have good reasons for thinking it might be nice to use these different class weights, but also it might work, it might not. We should treat it also as a hyperparameter and see from the data, does it actually improve things or not? Here in this small example, it didn't make any difference, but this is just a sample of the data set, so a sample of the sample. So we can see later in more detail how that works. Okay, good. We're making progress. Now we talked about hyperparameters. Now we'll talk about nested cross-validation. So how we can test hyperparameters in an even more robust way. So what we did is we found out how a set of hyperparameters work on a test data set. We could test each one of these individually. That would be complex. However, one thing that's super important is that if we've used documents to optimize something, in this case hyperparameters, it's no longer a valid test data set, and we can't use this test data set to estimate our model's performance on the new data set. So if we try every combination of hyperparameters on our test data set and we find that, okay, use class weights is 1, learning rate is this, number of epochs is this had a F1 score of 85, we can't say
Yeah. Okay. Do you have a USB? No, we don't have USBs. Okay, that's fine. I can just use this one. Okay. Okay, perfect. Good. Where was that? I was about to get into nested cross-validation, I think. Yeah, and I was just giving you the warning, don't make decisions on your test data. You need to split more times. You need to have training, validation, and test data. So you need to split your training into two parts and only optimize on the validation data. And we should never mix those up. So here I've just done a small little graph that shows what this is. Let's say we have 100 documents. first we split out the test data set, and then we split the training and the validation data set into two different parts.
Would you
Yes.
mind switching it back to the daytime one? Because I don't know what's taking this
Yes.
Not, I don't know, people would-
Okay. Maybe I can increase the size as well. No, I can't. Ah, perfect. Okay, good. So, yes, we split the data into three parts. Just for the code below, we're just going to make up a random number when we get the performance score, because we just want to just show the logic of the code, not to do nested cross validation yet. So here we're going to define a train function that does nothing, and an evaluation function that returns a random number between 0 and 1, just so we can follow then what we would do if that train function actually trained something. So what we would do is we would say for each p in parameter list, train the model on our subset of our training index with parameter p, and then append our scores and the result of evaluating that model on the validation data set. Then here we found the best parameters, which had an F1 score of 95. But remember, this is just a random number. Had these parameters. So this is how we would do it. And once we've done that, we have our best set of parameters. We can train a model on all of our training data that from the first split, so the training and the validation data set, and evaluate that on our test data set. Here, 59%, but also a random number. But it can be that that number is lower than the number you had before. In fact, it's rather likely. Okay, so that's the simplest version of choosing a set of parameters. However, each time we kind of sample data, then a random element of noise creeps into our process. And to reduce the influence of random noise, we can employ cross-validation in order to make our process more robust. And one way of doing this is splitting it into multiple training and validation splits. You can see that here, where we would say, okay, let's separate the test set, and then we'll do across 5 different folds. Each time, in each fold, for each set of parameters, we train, and then we find the set of parameters that performed best on average across these folds. But you can also already see that this increases the number of models that we have to calculate by k. So that's going to be a lot of models. And here we have this also then in this code. And we can go even one step further if we want to really increase the computational requirements. So our test data set, it's still only one sample from all of the possible test data sets that we could have created. And we could have had a different evaluation score had we picked another test data set. And so nested cross-validation allows us to use each labeled document we have once, making our estimate of generalization performance less susceptible to random noise. So we'll see how that works in a second, but it's useful when we have not much training, not much labeled data, but it's also very computationally intensive because we've multiplied the number of models we have to fit by k, and then by k again, and then also by k plus 1, but then I'll get to that in a second. What this looks like is instead like this. So we do an outer split. So we say, okay, this is our first test data set. And then we just do the same process as we had before. For each of these validation data sets, find the best set of models. Then assess our best model on this test data set. then do the same again, and the same again, and the same again, and the same again. And so we'll have each document will have been in our test set, in a test set 5 times. We'll have 5 estimates of generalization performance. And yes, that will be quite robust, but also very computationally intensive. However, this also doesn't deliver us one single best model. And if we want to find the best model, then we go through the whole process, just one more loop. Now, each time we take, this is the validation set, 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 and this one. And then we find the set of parameters that works best on those, which may be a different set of parameters that work best on the other ones. But what we've done instead is validate the hyperparameter selection process rather than any specific set of hyperparameters. Okay, I think that's probably enough nested cross-validation now. Just to say that this will take lots of resources. So the next slide is about how we can make this slightly more efficient. So what we did before was we did something called grid search, where we basically took a brute force approach to solving this problem. We tested every different combination of hyperparameters. In fact, there are many more combinations that we could have tested. And it's not a very clever way to kind of optimize everything. And there are clever ways to optimize things that kind of adjust the parameters that are being tested based on feedback from how well a certain set of parameters work. There are libraries to do this. So we can just set a space that we want to search and then do cross-validation using this this library, which will then test different, or we can do hyperparameter optimization during this library, which will test different combinations of parameters. If we want to do cross-validation using this library, we have to make some changes to our, we have to subclass something else where, because before we could take the average across different splits, but if we're optimizing like this, then we'll have across the different splits, not necessarily the same sets of hyperparameters. So we need to adjust it so on each split, it calculates then the model on then the 3 inner splits, and then we take the mean in there. We just have to adjust some of the code, but that's probably more detail than we need to look into. Okay, so now we're almost there with our pipeline. We just need to put everything together. And you'll see the full Python script in here and in here. And I think we don't need to go into it too much, but basically we just need to then run. We can run this script here, which will go over all of the different outcomes we're trying to predict. Inside this script, you can change the number of trials that we want to do with our opportunity thing. So if we have a large computational budget, we can have a large number of trials, a small number of trials, and we just run all of these models, all of these model fits, and then make predictions with the best model. So this is all in these scripts here. If we want to look at the trial data, Optuna saved this in a database called trials. Oops. Ooh. And you can see that we did 25 trials, but we stopped getting increases in our F1 score a little bit earlier than that, although it still kept getting a little bit better over time. I don't know whether if we'd done 50 trials, it would have continued going up. Possible, but probably. There are diminishing returns at least. And we've saved, our script has saved our final model performance in a JSON file. And this is then our final results. That our relevance classifier has an F1 score of 79%. The first level of our instrument category, 67%, and sector, 65%. So these are not terrible and not brilliant. This is also a subset of the data, but it's not too different from the results that we get in the paper. We get a little bit better because we have more data. Okay, so we now have a model. We know how well it works. All we need to do is look at the predictions. We've already made these predictions, and they're in a folder, results predictions. And we just need to merge then the predictions that we've made, which are saved in a NumPy format, with our database. And we end up with something like this, which is a database of 43,000 papers. And, oops, at the moment, it's just got the prediction for include. And this is now a number between 0 and 1. We can filter those where the prediction is higher than 0.5, and also merge in the other categories. Oops, sorry. And now we have then predictions for inclusion, then for all of the different instrument types. So now we have this data set, which is then the data set that we want to use in our further analysis. Okay. So nearly there. One final thing we want to do is embed the documents. So the way these kind of these language models work is by embedding documents. We use a slightly different model that has better embeddings that are more useful for this kind of work. We also have it, and there is a script that runs these embeddings. And we just need to load these, and we can see that for our 5,000 documents that we included in the end, there are 768 dimensions. We can't plot all of these dimensions, and so we use something called UMAP to do dimensionality reduction and get this into 2 dimensions. And then we have a nice cloud of points, which is our data. So now almost done. Just the final bits is how we make this interactive. So this is useful, this data set that we have, but the cloud of points isn't useful because it's just a cloud of points. However, if we can explore then those points and see what documents are related to each other, are close together in the multidimensional space, then this can become very useful. So we can make an interactive map. So maybe I skip this bit, which talks about how the different options we have for making interactive maps. Just to say that there are lots of different options, some mainly browser side, where you have to write a lot of JavaScript code, some server side, where you write R or Python code, some combinations of both. For data scientists, often we're more familiar with writing R and Python code. But if we're writing, then a browser can't interpret R or Python code, which means that it's limited how portable that is. So we might need to have a server. In any case, we're using Dash, which is a bit like Shiny for Python. So one thing we do is we put all of our data into a compact format that our app can read. So we just write various different files into the folder app assets and app data. Then we have a file called app.py where we define the layout. And then we have to define things called callbacks, which are functions that say what happens when someone clicks here. And it's basically we have an input, the bit that was interacted with. We can use states, which record some information about what things have been clicked on or what data is selected. And then we have an output, which says, what do we change? Here's one small example where we say, when we click on the button, download button, then we read the state table data and we put something in download data. And we run this function, which reads some data from our database, puts it into a data frame and writes it out to this download. So then we can read, then we can get the download, the data. We also have client-side callbacks. The reason why we need to have some of those is because if we're constantly sending 100,000 points to and from the browser and the server, that will be really hit a bottleneck. So we need to use define some things in JavaScript. They're defined in a file called assets.index. We need to actually in source.index. We need to compile JavaScript. It's quite complex that if you want to incorporate dependencies, then you need to write the file in one place and then put a function, run it through a function that writes a new file that incorporates then those dependencies. This is all described here. And then once we're all done with that, we can run python app.py, and maybe I'll see if my computer is happy to work again. It could just be running out of battery. Anyway, I can't show the version of the app with the data that we've just created, but I can show the normal app. Okay, so here we have then all of these points. This is now the whole data set, not just the sample that we worked with, but we've plotted them so that the documents that are close together semantically. And so we can see here all of these documents are about transport. We can use these filters like this. Transportation fuel subsidies, municipal emissions, carbon neutrality in California. We can zoom in on these and see the documents as well. We can read the whole documents in here. We can also do some text search. So let's say we want to look for Germany. If I can spell it, remember how to spell it. Okay. So here, okay, and that looks good. This wasn't working at some point. So this looks like something about Germany. Okay. So now we have we've made this app explorable. We can also download all of the data. And yeah, we can cut it in different ways. So we could say, I'm interested in Germany, the building sector. And then here we have then those papers that are about policy instruments on the building sector in Germany, and we can download them. Okay, I won't download them, but you can trust me that they're there. Okay, so that's now me done. I'll be happy to take any questions.
Well, first, thanks so much, Max, for this. Well,
Yes. Yeah, I mean, the paper isn't out yet, so the app is online. I mean, it's at the moment, it's got a placeholder, but it's there. It's apsys.mcc-berlin.net/climate policy instruments map. Or if you just go to apsys.mcc-berlin.net, then there'll be a link on there. Yes. And also, yeah, you can get there if you click on this little logo. This is our group website. And here we have climate policy instruments map and some various other interactive stuff as well.
Talk about something like this, but then more general. mean, the whole process, the whole pipeline. Yeah, collecting data and creating regular maps of any topic. Python or something.
Yeah, I mean, I think there are different cases. So there's some where when we have labeled data. So this is the case for when we have labeled data. And it's a luxury to have labeled data, and it took us a long time to get it. But then there are some maps where we don't have labeled data. We've produced some of those using topic modeling and stuff like that. And then there are some out there. So there's a paper that looked at the whole of bioarchive. So like all biology and lots of medicine papers, and put them all into also another big cloud of points. So there's a couple of different things out there. Yeah. But I think for this specific case where we have we have labeled data and then we want to train a model, I think basically now I've almost have it as a package by producing this tutorial. So this will help us like in a group then to reproduce this a little bit more easily. But I think also then at some point we can say, okay, if you have data in a similar format, then you can adjust things. And I did have some things where I've made some of the text in here like customizable, and the labels are also relatively customizable. So you could have data, you could have a different set of labels, and it would still work. Can't guarantee 100%, but I'm trying to make this also generic so that then like also within the group, let's say we have another project on climate and health, for example, we can produce then the same type of map with less effort involved. Yes,
Absolutely. And my question is a little bit just on your final step, but so for the callbacks of Dash, is the synchronicity of JavaScript an issue, or
is the what?
The synchronicity, so that it's async, sync JavaScript and Python?
I mean, some things work. The way some of them work is that you click on something, always there will be JavaScript involved, because this is about how the web page reacts to user input. So if you click on that, on this one, I think, no, that happens in the browser. So if we click on this one, all of the points, the cloud of points are stored in the browser. But I couldn't find a way to do text search in the browser very efficiently. So this happens on the server. So when we write Germany in here and click on OK, then JavaScript sends a message to our server. Our server says, OK, you want things about Germany, and you've also selected some things already. Then I'll do that filtering. And then it sends it back.
Thanks.
And you plan to do something with this data. And I think it's very useful. But then I'm thinking about, I don't know, when I come back, something like that. Then, wait, if we download this, it's the titles and the abstracts, or it's all the...
I sign in the titles and the abstracts. Yeah, but I mean, that could be then the basis for, I mean, we want to, the aim is that it's useful then for people doing a meta-analysis on regulatory instruments in the building sector, or the building sector and Germany, or some way of cutting across this data. We were like, the OECD were trying to produce a systematic review of all climate policy instruments in all sectors in about a year, and we were in contact with them, and then we thought that they could use the data, but in the end I think they're doing it rather manually, because I think then they're just like maybe not being quite so systematic with like a structured search, but just like looking for the papers that they know, because in the end, the time pressure is just like they have to get something out super fast. But in an ideal world, this kind of project would have been really useful to kind of tie in with the work that we'd created here. However, we have to think a little bit about like how we deal with uncertainty, because I mean, those F1 scores are not that high. One of the things that's quite nice is that, so in another map, we have a slider up at the top where you can say, okay, I don't want just the documents where the prediction is greater than 0.5, but I also want where it's greater than 0.2 or 0.3. Or conversely, you might say, I don't want to see anything that's not relevant, so I drag the slider over here, and then we only see stuff that the classifier is very sure it's relevant. So I think we can make that, we can make, with a bit of additional work, we can make that work a little bit better. Because I think for different applications, we have different preferences for precision recall. But one thing that I'm trying to think through more systematically at the moment is like also uncertainty about those F1 scores. So if we say that F1 score is 0.7, and then we've calculated phi, so we can then do this, we can report the mean and the standard distribution, but what's our kind of confidence interval? How's that related to the test data, the size of the test data? Somehow I feel like we don't often report confidence intervals around those, but if we want to use it for kind of critical applications where we care a lot about missing stuff, then I think we should.
Quick questions on the engineering side, because I think you mentioned that you screen the data as well with analytics, whether the records or something like this.
Mm-hmm.
How do you store them on your server? You store them in a file or store them? And what kind of process do you do to basically query these? Because I can imagine that's quite additionally expensive to query these big data sets for information about the trading on them. And then what is like the information?
Mm-hmm. Yeah, so we don't need to do any scraping. We just download the snapshot. So it's simple to get it, and we use something called Solar, which is like so it comes as CSV files, I think, or yeah, I think it comes as compressed CSV files. And also there's a lot more data than we use. So like there's also the whole network. So which paper cited which paper, and that's the really big data, because then that's billions of edges already. But we use Solar, and basically you just have to pass Solar a load of data and then tell it to index it. And actually it works pretty well on our server, that we can query it really nicely. And Solar already provides like a nice interface for working on queries. So that was actually easier than we thought. We also made, we spent a lot of time trying to put it in a Postgres server, which we thought would be simpler than Solar for some reason. But it really wasn't, and trying to do text queries was so slow, it really just wouldn't work. And then we used Solar, and it just worked like that. It was super easy.
I was going to ask you, because you touched on it earlier, the potential for using ChatGPT or some other large language model for classification. Kind of conversation looks like there. Some issues with it.
Yeah, I mean, so we couldn't use ChatGPT unless we had a very large budget to produce all of these hundreds of thousands of labels. That would be too much. It would take a long time, and it would be very expensive. The question is, could we substitute or complement some of the human labeled data with ChatGPT labeled data? And I think there are a couple of modalities that could work with. So the most appealing is we simply say, ChatGPT, you do all of the coding now. And then we simply have to decide what's our ChatGPT budget? How many documents do we code with ChatGPT? For that to be okay, for me to be comfortable with that, I would want to, ideally in each project, or if not in several projects, to have evaluated how often ChatGPT agrees with the process that we had before, which I'm confident in. Of course, it's not perfect. I don't know yet what would be my threshold for how many times and how many different data sets I would have to see it be what level of F1 score for me to say, okay, now we don't need to code things by hand anymore. I think there's also a slight social process that in doing the coding, you're also learning something. So that's like if you completely automate everything, then you're no longer kind of engaging them with the content to as great a degree, and I think the work will not be as good. But then the other question is, well, what if we use ChatGPT as a second coder? Instead of double coding everything with 2 humans, we did 1 human, 1 language model. And then could we do twice as many? Could we then have coded 5,000 documents? Would that have then increased the performance? And then also, okay, what if we did 2,500 documents like this, and then we supplemented it with 3,000 ChatGPT documents? I think we just need to do quite a lot of experiments to understand under what conditions it improves. So some combination of all of those things might improve then the model that we can train. I don't know which combination, but it would be super interesting to find out. And I think that's something that we need to, it requires careful evaluation, but that's something we need to do.
There's a lot of focus on the text itself telling you something about all those classes, but you mentioned the networks, and I'm the way scientific research is published, but also structured, the incentives for citations work, that must be quite predictive, right? So if one paper cites the other, say even when you there's a text component where it cites it as a central part of a paper, maybe multiple times. Have you tried and implement this network feature, citation networks, but on a more general level, meta aspects of the paper, right? Author features, and you can tell the same author publishes 10 papers, it's probably about similar stuff.
Mm-hmm.
Or other, I don't know, other features like journal level information, stuff like that.
Yeah. So actually the model that we used for doing the embeddings was trained, it's like BERT, in that it has this large language model type. And then it also had a second pre-training task, which was a contrastive learning task, which was basically saying which sentences were, there was a set of sentences and their similarity, and it was trained to figure that out, basically. And the paper that, the model that we used to do these embeddings was called SciNCL, and it was trained on scientific texts, titles and abstracts, with a contrasted learning task based on citation patterns. So if papers cited each other, then it's kind of increased the kind of supervised data that we could use for this model. And for reasons I don't quite understand, this having this extra contrastive learning part means that then the embeddings are nicer to use. But it also means that it's kind of trained to understand how scientific texts are similar and not similar to each other, which should improve how well the model works on new text when you fine-tune it. However, when you fine-tune it, you just pass the text to the model. Yeah, I think it's complex then to incorporate then multiple features. I don't know how we would do that as part of this same model. I mean, one thing could be to try and have some ensembles of models that use different aspects. So some using text and some using the network, some using combinations. Yeah, but I think it would be super interesting. We don't look into the data too much in this paper, this type of data. Yeah, but I think the citation network is super interesting. Definitely.
All right, already over time. Again, thanks so much, Matt, for being with us. I guess we have more questions. There'll be a chance to follow up and maybe use some of your code to actually carry that
good.
into other domains.
Yeah, you can also, if you find a problem, you can also click on open an issue and I'll get an email.
Don't regret that.
Yeah, exactly. I didn't say I would respond to it. And also the GitHub goes to my personal email, which I don't feel any responsibility to keep up to date with, not like the work email. Okay, good.